Here I am going to go over the calculations for the Carbonates Lab. So I'm starting off with my table 1 here, and then this over here is table 2. So this is the mass of the beaker by itself, and you'll notice that both this column and this column are the same because it is just the mass of the beaker. So when we started the lab, we started with a beaker, we weighed it out, and then we added our carbonate to it. And so I just took the numbers that were recorded in table 1 and just transferred it to table 2. So then I was able to calculate, add some carbonate, and then calculate the mass of the carbonate that was actually added to the beaker. And then this over here, the mass of the product, this is the actual mass that we determined by weighing the product once it had fully cooled and come out of the oven. And so we are going to kind of go through these calculations, and the way I'm going to do this is I'm going to very slowly walk through reaction A, then I'm going to get you started on reaction B, and finally I will leave reaction C for you. However, I will then post the I will give you the data for the calculations as they would turn out with my data. So in other words, you will get a full-on set of answers for all 3 of the reactions, and then you can also practice with my data if you would like to have extra practice if you get stuck and are struggling with your own. Okay, so first off, we're going to balance the equation. So we can see that we have a reaction where we take our carbonate, and this is a solid carbonate here, and so this is what we put into our beaker, and then this is the aqueous acid solution that we added to it. And then after it reacted fully, we lost some gas, and then we had salt and water, and then we hoped to boil off some of the water and then fully dry our compound. So we're starting off by looking at this reaction, and we see that we have over on both sides of the equation, we've got a sodium here and a sodium here. And then we have an HCl here and a Cl here. Okay, so far the sodium and chloride are balanced. So then we can look at our hydrogen. So we have a 1 hydrogen, 2 hydrogens, and we have 2 hydrogens here. And then we have 1 carbon, and we see 1 carbon. And then we have 3 oxygens, and we've got 2 plus 1, so that's 3. So this reaction is actually balanced as is. So we don't have to add any coefficients. So you could put 1s on those blank lines or just leave them as is. Okay, so now we need to figure out the mass of the sodium bicarbonate and the mass of the sodium chloride so that we can convert the masses that we weighed out in the lab to moles. So we get the molar masses by adding up the molar mass of each element on the periodic table that makes up the compound. And so if we add a sodium, a hydrogen, a carbon, and 3 oxygens, then we get 84.007 grams of sodium bicarbonate per mole. And then for sodium chloride is 58.44 grams per mole. And so now that we know what the molar mass of sodium bicarbonate and sodium chloride are, we're ready to use stoichiometry to calculate our predicted yield. So first step is to go from mass of our starting compound to moles of our starting compound, because remember that we cannot just compare masses since these compounds have different makeups, and we want to go by moles because that's how we're going to know how much product we can expect to form, because it's the individual atoms that are mattering, not how much they weigh. So we take our mass of sodium bicarbonate, and we started with 0.276 grams. So I have 0.276 grams of sodium bicarbonate. Oops, I wrote nitrogen. Sodium bicarbonate. And then we're going to multiply that by 1 mole of sodium bicarbonate to every 84.007 grams. And then what happens is we're canceling our units, so we're canceling grams, and we're left with moles. If you get confused and you're not sure if you multiply or divide, just set it up so that you have the masses canceling and you're left with the units that you want. Because the question is asking you, convert mass to moles. So you're going to start with mass, and then you want moles to be your final units. And so all I have to do is take my initial mass, and I'm going to divide it by the molar mass, and then I get 0.003285. Now I'm going to keep 4 sig figs here because even though our scale only goes to the third decimal place, only 3 sig figs, I want to make sure that I'm reserving a little bit so I'm not losing a lot of product to rounding. All right, so then I look at my balanced equation, and in my balanced equation, I see that for every 1 mole of sodium bicarbonate I should get 1 mole of sodium chloride. And so we don't always need to set up this ratio if it's a 1-to-1, but I'm going to write it out so that you can see this. And so if we have our moles, and this is of sodium bicarbonate, right? So we have our NaHCO3. And then we're going to multiply that by our mole ratio conversion factor. And so we know that for every 1 mole of NaCl, we need 1 mole of sodium bicarbonate. So even though we're not really changing the value of the number, I want to show you why that works. And so if this isn't 1-to-1, we're going to do that. We're going to do this step for all 3. Okay, so then I can just keep the same value because this number 0.003285 multiplied by 1 is 0.003285 moles of sodium chloride. And now we have to convert the moles of sodium chloride to the mass. And the reason we have to do this is because we don't actually have a way to measure moles in the lab directly. We have to measure mass using our analytical balance and then convert to moles. And so we can't just do mass to mass because obviously it's the mole ratio that's important for the reaction. And then we have to convert back to mass to know if we got the amount of product we expected to get. So I'm going to take my 0.003285 moles of sodium chloride, and I'm going to multiply that by 58.44 grams per mole of NaCl, and my moles of NaCl are going to cancel. And so I just have to take my answer and then multiply it by the molar mass, and I get 0.192 grams of NaCl. Okay, now it is time to calculate our percent yield. And so what we're going to do is divide the actual mass of product that we measured in the lab divided by the amount we expected to get. And so this expected yield right here, this is the amount of sodium chloride we would get back if the reaction went theoretically perfectly. So every mole of sodium bicarbonate was converted to a mole of NaCl with perfect efficiency, and no product was lost, no water stayed in the beaker, everything went perfectly. And so we need to look at our actual mass and our expected mass. So the actual mass is what you recorded. And so we have to look back at our table 2, and we see that the mass of the product for beaker A, so the sodium chloride I got from the sodium bicarbonate reaction, was 0.234 grams. So my actual mass that I'm going to put in there is 0.234. And then I look at my theoretical yield, and that's what I did in step 5. And I'm going to put that in the denominator, and that is 0.192 grams. And then I'm going to multiply by 100. And what you'll notice is my yield was higher than I expected. But that's okay, because all we're trying to do is practice and then also look at the amount or look at the results that we get and try and explain them. And so I'm getting about 122% yield here. So we'll talk about reasons that could have happened in a minute. Before we start to draw conclusions about our lab, I would like to at least set up parts of reaction B, and then I will go back and enter all of the data and we can talk about our conclusions. So here we have sodium carbonate and hydrochloric acid, and so this, we shouldn't have a hydrogen there. And so what we actually should have over here is Na2CO3 plus HCl. And this is our solid, this is our aqueous. And we need to balance it. We need to predict the products and balance the equation. And so we're going to use pretty much the same formula we used before, although we're going to need to work to balance this a little differently than we did so in the first reaction. So we're still going to have CO2 gas, liquid water, and then the salt, the sodium chloride. And we are going to look at here, and we see that we have 2 sodiums on this side and only 1 over here. And so I'm actually going to take since I've got 2, I'm going to put a 2 in front of the NaCl. And now I see that I have 2 NaCl, so then I'm going to come over here and look at this, and I'm going to put a 2 here. All right, so now my sodiums and my chlorides are balanced, and my oxygens are balanced. I've still got 3 oxygens here, and 2, 3. And then I have 2 hydrogens, and I have these 2 hydrogens here, and then I have the 1 carbon. And so now we're balanced. So I'm going to take the moles of sodium carbonate and convert that to mass using the same format that I did before, and I'm going to follow that through and do all of these calculations. So I recommend pausing the video and trying this yourself using the data that I have at the top of the page in that table, and see if you get the same answers I do so that you can demonstrate to yourself that you understand how to do these before you move on and try to do your own calculations. So here are the results of my calculations. I started off by calculating the moles of sodium carbonate, and so I took my initial mass of sodium carbonate and I multiplied it by this conversion factor. So essentially I'm taking the mass of this and I'm dividing it by 106, and then I'm getting the moles of sodium carbonate. Now this is where the reaction you have to pay attention to the balanced equation here. It's different from the one that the first reaction we did. So we see that we have moles of sodium carbonate, but if we look up here at our balanced equation, we have 1 mole of sodium carbonate, and that will make 2 moles of sodium chloride. And so that means that if we set up this is that molar ratio that is a conversion factor. So we're starting off with 0.001849 moles of sodium carbonate, and then we have to multiply that by 2 because you get 2 moles of NaCl for every 1 mole of this. And so now you have moles of NaCl. And once you've done this, once you've done this step here, you do not need to worry about the fact that there's a 2 here. We have taken into account you get 2 moles of sodium chloride for every 1 mole of sodium carbonate by this step here. And so you're not going to multiply anything else by 2 or divide anything else by 2. Once you know how many moles of sodium chloride you expect to get, you just keep this number and then continue the calculations as we did before. So we take the moles of sodium chloride and we multiply it by the molar mass. So we have moles of sodium chloride, and that's going to cancel out, and we're going to get this number here multiplied by 58.44, and then we get our theoretical yield of 0.2161 grams of sodium chloride. And then much like we did before, we take our mass and we divide it by the we take our actual yield and we divide it by our theoretical yield. So in this case, unlike in our last one, we actually got less product than we expected. So we only got 0.181 grams out instead of the 0.216 that we expected. And so our yield is about 84% or 85%. So for our last one, you are going to do this one mostly independently. Of course, if you get stuck, you are welcome to contact a tutor or ask questions of me during student hours or during class or before class next week. But the one thing I do want to talk about is we're going to use the same steps. And so the whole flow chart, if you want to think about it that way, is you're going to start off with the mass of the calcium carbonate, because that's our third reaction, right? So you're going to have mass of calcium carbonate. And then what you have to do is convert that mass of calcium carbonate to moles of calcium carbonate. And then once you've done that, you have to use that ratio, that stoichiometric ratio, as a conversion factor to go from moles of calcium carbonate to moles of product. And then once you know the moles of product, it is not sodium chloride yet, but whatever that is, then you're going to go from moles of that to the mass of the product. And once you know the mass, then you calculate your percent yield. And so I'm going to show you my final table. So here we have the amount of carbonate that I started with. So these data here are from my table 1. And then these here were all calculated. So these are calculated. And then this here is from table 2. And then again, percent yield is calculated. So we have, table 1 data, we have table 2 data, and then we have calculated here. Okay. So then I want to look at these percent yields right here. So our question 15 for the reactions to comment on our percent yield. So we're thinking like, well, why is it too high or too low? And I'm really saying, give yourself an error of like 15% just because you don't really know. I mean, if you're real close, like you're not getting it exactly at 100, but that just doesn't happen. So practically speaking, so if you get like 96%, you would say that you have a reasonable assumption that your product is fairly pure and you turned most of your reactant into product. But in our example here, we have a yield of 122%. And so the yield is too high. So what might make our yield too high? So the biggest thing is you have something in your container that shouldn't be in your container. So look at the protocol. Think about all of the steps that you went through to remove things that shouldn't be in that beaker before you weighed your product. And that can give you an idea of what might cause a high percent yield. Now, for a low percent yield, you want to think about, did your reaction go to completion? Because what happens if you're supposed to get 2 moles of NaCl and you're only supposed to start off with 1 mole of sodium carbonate? What happens if that reaction doesn't go to completion? Is there a side reaction that can happen? Did you spill something? So there's all kinds of things you can think of that might cause a low yield. Now, you need to make sure that you are offering an explanation on why the yield could have been too low if your yield was actually too low. And then again, offer an explanation on why the yield could be too high if the yield was too high. You don't want to offer an explanation like, I spilled some of my carbonate and so that's why my yield was too high. That doesn't make sense. So you need to have it match kind of what you thought could have happened. And then here we have the sodium hydrogen carbonate. And so this is kind of one of the things that you can do if you've got sodium bicarbonate and you heat it in your oven, you'll get some sodium or sodium bicarbonate, you'll get sodium carbonate. So this here, this is baking soda and this is baking powder. So baking powder is a mixture of the baking soda and then the sodium bicarbonate, which is pure sodium bicarbonate is called washing soda. And so you want to use the law of conservation of mass to predict what this product is. So look at your reaction here and what's missing from, this side that could help balance this. That's kind of what you want to think about. All right, so if you have any further questions about this, please reach out for help. You may go to the tutoring center, you may ask the tutor, you may ask the SI leader. Don't suffer in silence. Please reach out. Send me a Canvas message and I will get back to you as soon as I can. And if you are still having trouble after all that, please email me and we can set up an appointment to meet together on Monday or Tuesday when I get back from being out of town. All right. Happy studying.